You ever seen that before?
Yeah.
Not happy I've seen it before, but I've seen it before. Last year, we showed this to you a few times. Last chapter, we showed it to you a few times. And what have I always said when we showed that to you? You're going to need it. We're going to use it. We're going to use it a lot. At some point. What time it is? It's at some point. Yeah. And you can see it here. So what does this really represent? From what we've talked about here, what does this represent? Slope. The slope. The slope of this line. Now remember, what's our goal? Find the slope of the tangent line, and to get the slope of the tangent line, we want to make okay, where's the second point? Where do we want the second point to be? Do we want that second point to be here? So what could we change to make it closer? Not x, but delta x. Right? Right now, delta x is this, which is nice and it's helpful. And like we said, it gives us something in the general ballpark. But as we also said, the smaller we make delta x, the better the approximation. So the smaller we make delta x, the better. All right? And so you can kind of see what they're doing here with their stuff. What they're doing is what we just talked about. And what they're trying to show you is what we just said, which is the smaller we make delta x, the better we're going to be. How small can we make delta x?
Very.
We make it 1?
Yeah.
We make it smaller than 1? How small? How small do I want?
Anything more than 0.
As long as it's above 0. So 0.1, 0.01, 0.0001, 0.00001, etc. Yeah. And that's what we're going to be doing in this chapter. We're going to be making delta x as small as we can possibly make it. And we're going to see the differences when we have a small delta x as opposed to when we have a very small delta x. We don't want a big delta x. Is that fair? We don't want, I mean, if it's big, this approximation doesn't really help us to find that. Okay? So we're not even going to talk about a delta x being big because that doesn't help us. We will talk about delta x being small, and then we'll talk about it being very small. And then we might even talk about it being very, very small. And so here's the type of thing that we're going to be talking about. Okay? So we want to talk about basically the equation of the line that is tangent to y equals x squared. Is what I'm saying making sense at all, or am I talking Greek? Okay. If it's not making sense, tell me, all right? What does f of x equals x squared look like? It's a parabola with a vertex at
0,
0, 0. It also goes through the points 1, 1,
negative 1,
2, 4, negative 1, 1, negative 2, 4, etc. Right? We want to find the equation of the line tangent to y equals x squared at the point 1, 1. Is it important for us to define that point?
Yeah.
Because otherwise, I mean, we could have a tangent there, we could have a tangent there, we could have a tangent down here, and the lines would be 100% totally different. Some slopes would be positive, some slopes would be negative, so we have to identify that point. So, at the point 1, 1, so the point 1, 1 is going to be somewhere around there. So what do we need to be able to find the equation of the line tangent at that point? Another point that is close, very close, really, really close. And so what do? Well, what they're talking to us about here is, let's try our second point, because we know the first point, right? The first point's 1, 1. Let's try 1.5, comma, 1.5. Well, they just call it f of 1.5 to make it easier. Okay, would that be helpful? A little bit. Would that be more helpful? Would that be more helpful? Yes. Would that? And then, wow, look at this. How close are we right now?
Very.
We're really stinking close, which would give us a really good approximation. This would give us a second point. We could find the slope between them, and then we basically be able to find the equation of the tangent line at that point. Reasonable? That's where we're going with all this. Everything else we do here is kind of following up on that. Okay. Now, that's the tangent line. That's how we do that. Okay. The other big thing that we're going to talk about as calculus gets started is what they call the area problem. And what we're really going to be looking to do is to find the area under a curve. Okay. So how do we feel about that? The thoughts of the tangent line thing. General idea, okay? Okay, cool. Yeah. Yes. This chapter, chapter 1, is going to be a lot of work. It's going to be a lot of repetitive stuff. And I'm going to tell you right now, it's going to annoy you, at least to some extent. Okay? I ask you to do what you're supposed to do in chapter 1. And then once we get to chapter 2, you'll see why, and it will all pay off. Okay? So, and the amount of work will go down dramatically. Okay? But if you do what you got to do in chapter 1, then chapter 2 is going to be a lot easier. Okay? All right. So we want to find the area under the curve. So let's start with this same picture out here like we did on the other one. Okay? And we want to find this. Now, here's the problem. I don't know how to find the area under a curve. I do know how to find the area of a rectangle. I'm good at that. So if this were just one big rectangle, I can do that, right? Okay. How do we find the area of the rectangle?
Length times width.
Length times width, base times height, whichever way you want to talk about it, makes no difference. What's the base here?
AB.
The distance from A to B. How could we write that?
Delta A.
B minus A. Does that make sense? What's the height?
A2.
So basically the height goes from here to here, or better yet, probably from here to here. How can we write that top point? F of B. Good. Does that make sense? That's F of B. And then what's this point? Well, but F of B indicates what type of a coordinate? An X or a Y? A Y. So we would want the Y there. What's the Y there? 0. So F of B minus 0, something like that. How is that for an approximation as to the area under the curve?
It's way over.
It's not totally horrendous, but it's not very good. Is that fair? Okay. So what could we do to make it better? Well, how about this? Let's do 2 rectangles. And let's make one of the rectangles from here to here, and the other rectangle from here to here. So maybe we go up to here, we go over and down. And so now we have that. And then for the other rectangle, we go up to here, and we go over, and we go down. Are the two green rectangles a better approximation for the area under the curve than the one blue rectangle?
Yes.
Yes, we would all agree there? Okay, cool, so we're getting better. What would make it even better?
More rectangles.
More rectangles, right? More rectangles, okay? So let's say we did 4 rectangles instead of 2. So now we go to here, we go over, we go down, okay? Then we go to here, we go over, we go down. Then we go from here, we go over, and we go down. And then we go here, and we go over, and we go down. Better approximation. Better approximation. What would make it better? More rectangles. And the more rectangles we make, logically, the better our approximation is going to be. Is that fair? So, how do we deal with more rectangles? Well, we did b minus a here, correct? Okay. And then we did f of b minus 0, which we'll talk about in a minute. Okay. But what's another way, considering what we've talked about already today, what's another way to talk about that distance from b to a?
Delta.
Delta x. Delta x? We could call this distance between here and here delta x. So that would be b minus a with our original. But with the purple rectangles, no, with the green rectangles, I'm sorry. Color coding is great as long as you stay with it. With the green rectangles, what happened to delta x? It cut in half. So now delta x is only that. Right? And then with the purple rectangles, delta x is now that. It's a bad delta. So once again, what's our goal? To make delta x as small as possible. The smaller we make delta x, the better the approximation we're going to get. Okay? So here, they're doing this using 8 rectangles. Here they did 4 and all that stuff. Okay? And you can see, and I mean, you know what's going to happen, right? The more rectangles, the better the approximation. As simple as that. All right. So let's cut down here. They talk about exploration, the graph bounded by. Okay. And I want to talk about this one more time, and then I'm pretty much done with this section 1.1. Which is why I wanted to make sure that I talked about section 1.1. Because are you picking up on where we're going with it? Okay, and that's the goal. As long as you can pick up where we're going. So I want to go back. Oh, there's not a chance in the world I'm going to be able to fit this in the right spot. Is there? That's pretty good. I'll take it. The purple rectangles, the last one we did. Let's see if I can even, I don't want to give it. The purple rectangles, is that an exact approximation?
No.
I agree. Is it, will the approximation be greater than or less than the actual area under the curve?
Greater than.
Greater than, I would agree with that. Because you have like this area up in here, that's part of the rectangle that's not inside the curve. Here I just kind of drew that badly, but you might have this little area in there that shouldn't be, but then here you have this area. So you have a lot of areas that are too much and one little dinky area that's too little, right? So this is going to be too big an approximation. But what we did here is we took the right side of the curve and drew the rectangle. What would happen if instead of doing the right side of the curve and drawing the rectangle from there, what if we used the left side of the curve to draw the rectangle? And I'll show you what I mean. Okay. You know that the purple ones, they would be too big, right? Or the approximation would be too much? Okay. I'm going to erase that if you don't mind. And we're going to try it again using the left side of the rectangle to draw the curve. So now, let's see. We still have there. So now, we're going to come up and we're going to do from this point over and down. And then from the left side and over and down. And then from there and over and down. And then from there and over and down. Do you see the difference? Do you see what I'm doing there? Okay. Tell me about that approximation. That's too small, right? It's too low. Because we have this area that's under the curve that we don't get. We get this area that's under the curve that we don't get. We get this area that's under the curve that we don't get. Oh, and I didn't line that up well at all, but you know what I'm getting at. Okay? So another thing that we will have to pay attention to is how we draw our rectangles. Are we drawing them using the left side of the rectangle or the right side of the rectangle? And that's the only point I'm trying to make here, is that the side that we use will make a difference in terms of whether our approximation is too great or our approximation is too small. Does that make sense? Are there questions? Okay, now as you can see, okay, that's the bottom of the page, and that's the end. The next page is your homework. Okay, so let's talk, wrong page, there we go. Let's talk a little bit about what your homework is like for section 1.1, if that's okay. Okay, so the first couple of questions, you have 5 and 6. Determine whether you can find the area of the region using pre-calculus. If you can, find it. If the problem seems to require calculus, explain your reasoning and use a graphical or numerical approach to estimate the solution. Are those reasonable questions? Okay, this isn't a huge step up, right? For the first one, is this a calculus problem or a pre-calc problem?
Pre-calc.
Why? Yeah, because there are no curves. Whereas the second one is a calculus problem and stuff like that. All right, then we move along. We come over here. Oh, and it's the same question on number 10. Oop, where am I? I lost it. Yep. So is 10, let's see, yeah. Can you find the area under the curve, just this area here? Is this a calculus or a pre-calc problem?
Pre-calc.
That's a what?
Because it's just a square.
It's curved, but it's a square.
Yeah, I'm gonna call that a calculus problem because of the curve in there. But yes, I see what you're saying, and I don't entirely disagree.
Area of it is like shape. It has to be this curve is out.
Yeah, basically. Then they're going to start to talk about secant lines. Okay, do you remember what secant lines are?
Pass through both.
Yeah, it goes through the 2 points. Okay, so if we're using f of x equals square root of x, and the point 4, 2 on this graph, then graph f and the secant lines passing through 4, 2, and if x is 1, x is 3, x is 5. So you're going to have to find 3, well, you're just graphing there, finding the slope for each secant line, and then we want to use that to estimate the slope of the tangent line in the graph at that point. So you'll see what it looks like. You're basically going to draw the graph, you're going to draw 3 secant lines, and you're going to find the slope of all of them, and then try to guess what you think the slope will be at that specific point. You'll see when you do that. that's the type of thing that we're going to do here. For now, we're using the information that we talked about today to help guess. And the smaller we make our delta x's, you'll see, the better our guesses will be. Okay? Questions? At this moment, according to the calendar, we're a day behind. That's okay. We'll get that during the 1-3 period. So still expect the quiz to be next Friday. And then we'll start 1-2 tomorrow. So we'll do 1-2 tomorrow and Monday. We'll do 1-3 Tuesday and Wednesday. We'll review Thursday, quiz Friday. Sound okay? Tell me about what we talked about today. Does that make you feel better or intimidate you more, or it just is?